This conference will now be recorded.
Greetings to one and all present here. It gives me immense warmth and great pleasure to grace all of your presence in the interest of the webinar. To begin with the webinar, I would like to call our Honorable DG Sir to address the webinar.
Today's guest speaker, Mr. Temble, we are very thankful to you that you have given us time. On behalf of IST family, I must give my big thank to you, and we are looking forward for further your mentorship with our students, how we should proceed further in mechanical engineering. It's a great initiative by HOD sir, and I'm quite happy that number of students from the first year to final year are attending this webinar. Looking forward, the new era in technology. Now this is a time when mechanical engineering must offer the addition of new subjects, or you may say new version of old subjects. Nanotechnology, clean technology, and many other fields like design has made an entry into mechanical engineering, I think, a decade back, and got itself manipulated in different forms. Among these technologies are micro and nanoscale fabrication processes also. So modern mechanical engineers must navigate virtual design environment and be ready to adopt in computing, so that they must play a significant role in future in the development of information technology. I was going through various technologies, emerging technologies in mechanical engineering. Earlier also I've spoken about it and listed out. Again, for the reference of all of you, that we have to change the structure and course curriculum of mechanical engineering. And next year you will see a different form of mechanical engineering, and we will offer a different course altogether to our new students who are coming up in the first year, a different type of subject in mechanical engineering. But for those who are here, it is our bounden duty that we must give them the latest. Because mechanical engineering department is facing a huge challenge with reference to the job. The main problem is that we are not able to provide skills. I'm not talking about IST as a whole, but as all the colleges we are not making our students ready for industry 4.0, for which we are talking it about. Apart from additive manufacturing, just 4D printing technology, and one more branch I was going through, what is called NEMS, Nano Electromechanical System, Hyperloop technology, computational fluid dynamics. And very interestingly, I was talking to CS department, then I was telling them that there is a IoT, Internet of Things. But now they are doing IOB, Internet of Behavioral IoT. They are seeing the behavior of a person and suggesting the web. It's like that. You can also include Industrial Internet of Things, IIoT, Industrial Internet of Things, which is also will come later on. In civil and computer science, it is Internet of Things of behavior. You can start IIoT. Likewise, beamed energy propulsion, advancement in gas turbine technology. So you have lots of scope in mechanical engineering, because mechanical engineering is a core branch. The point is that our students should be well versed in the softwares available and what is the expectation of industry. So we should have a liaison between academia vis-a-vis industry. In fact, I have given one suggestion that the industry people should come here for 1 month. They can take sabbatical leave and teach our students. Likewise, our faculty can go to the industry and see what they are doing. I'm ready to give them 2 months leave, 3 months leave, sabbatical leave with pay. If they can involve themselves in any industry and see what they are doing and what are their requirements. There is no dearth of employment. If you are qualified, you will definitely get the employment. So academic institutions are failing in their duty, that they are not giving them that much of skill to their students, what is needed. So it's a high time, and I'm very happy that Dr. Vikram Singh ji is a very qualified person, and likewise other faculty members. But my only request to all the faculty members and to the students, that you have to do hard work, because for mechanical engineering, according to me, 5 things are more important apart from these technology. That you should have a problem solving skill, because mechanical engineering deal with the complex puzzles between you and the perfect mechanical product or device or system. Second phenomena which must be inculcated in your personality is creativity. And third is communication with your team, because communication is needed. Even more important when you are explaining your clients or your co-members how to use your product and solutions. So must emphasize on English communication also. You think why mechanical engineering should learn engineering English? No, it is must, because you have to communicate. Once you will go to any advanced industry, you can ask our guest speaker. Likewise, teamwork. The team you should do, and you can produce some kind of model or projects working together. I'm very happy that all of you were working in our project in workshop, and we should initiate more projects where teamwork should come up. And most important thing, I don't know whether I'm correct or not, mathematical skill. According to me, calculus or statistics and mathematical principles is also must for any engineering branch, and it is more particularly for mechanical engineering. I will not take much of your time. I again thank our guest speaker and all my blessings to all my students. Thank you very much.
Thank you, sir, for your warm words. Now, I would like to call our head of SIG, Additive Manufacturing, Professor Naman Gandhi, sir, to brief about the event.
A very good morning to one and all present here. Respected DG sir, Principal sir, HOD sir, faculty, staff members and dear students. जैसा कि आप सबको पता है कि आज हम लोग मेटल एडिटिव मैन्युफैक्चरिंग SIG के बारे में एक्सपर्ट लेक्चर रखा है। जैसा कि सर ने बताया कि नई टेक्नोलॉजी क्यों सीखना जरूरी है, तो बस मैं ये कहना चाहूंगा कि जो 2010 में मैंने इंजीनियरिंग पढ़ी थी वही मैं आपको आज पढ़ा रहा हूँ, और वही HOD सर ने जो 2000 में पढ़ी थी, मुकेश शर्मा सर ने 1996 में पढ़ी थी, तब भी वही सिलेबस था जो आज है। इसका मतलब जो टेक्नोलॉजी 1996 में जो थी, क्या आज तो वो नहीं है? बहुत ज्यादा सिग्निफिकेंट चेंज आ गया है। हर दिन टेक्नोलॉजी बदल रही है। जितना पिछले 5000 वर्षों में डेवलपमेंट नहीं हुआ है, उतना पिछले 150 वर्षों में हुआ है। तो लगातार टेक्नोलॉजी चेंज हो रही है। तो क्या स्टूडेंट्स जो अगर सब्जेक्ट्स पढ़कर ही कोई जॉब पा सकते हैं? क्या नहीं पा सकते। सब्जेक्ट्स पढ़ना पड़ेगा, वो है फंडामेंटल्स। बस फंडामेंटल्स जो आपकी नींव है, लेकिन नींव के बाद आपको मकान भी तो बनाना है। तो उसके लिए हमको लेटेस्ट टेक्नोलॉजी सीखना बहुत जरूरी है। और अगर मैं बात करूं 3D प्रिंटिंग, एडिटिव मैन्युफैक्चरिंग की, तो जितना स्कोप मुझे इसमें नजर आता है उतना शायद किसी फील्ड में नहीं है। आज नासा भी स्पेस के अंदर 3D प्रिंटर लेके जाते हैं कि उनको कुछ भी जरूरत पड़ती है वहां पर तो प्रिंट कर सकते हैं। भविष्य में ऐसा होगा जैसे अभी आप लोगों को कुछ प्रिंट आउट निकालने होते हैं, आप लोग क्या करते हो, वर्ड फाइल बनाते हो, पेन ड्राइव लगाते हो, साइबर कैफे में गए और प्रिंट आउट निकाल के लेके आ गए। सिमिलरली डिट्टो क्या होगा कि आप लोग अपनी डिजाइन बनाएंगे, डिजाइन की सॉफ्ट कॉपी तैयार करेंगे, आप जाएंगे 3D प्रिंटर के पास में और जो 3D प्रिंटर वाला है आपको प्रोडक्ट बना के दे देगा। वही चीज आज विप्रो 3D कर रही है। विप्रो 3D जो कंपनी है वो भारत की पहली मेटल एडिटिव मैन्युफैक्चरिंग कंपनी है। आज ये इसरो के लिए, DRDO के लिए और बहुत सारे गवर्नमेंट ऑर्गेनाइजेशन के लिए मेटल के प्रोडक्ट्स बनाती है जो लेटेस्ट टेक्नोलॉजी पे डिपेंड है। इसी के साथ साथ अगर हम मेडिकल फील्ड में जाए तो वहां पर भी हर बड़े से बड़े हॉस्पिटल में आपको 3D प्रिंटर्स मिलेंगे, क्योंकि अगर कोई प्रोस्थेटिक्स है या कोई पार्ट्स है तो उसको आप 3D स्कैन करके एक्चुअल डायमेंशन में कन्वर्ट कर इसका डिजाइन बनाकर आप उसका प्रोडक्ट निकाल सकते हो। वही बात अभी 2 महीने पहले चाइना ने एक बिल्डिंग खड़ी कर दी पूरी, 2 दिन के अंदर एक बहुत बड़ी इमारत बना दी। कुछ नहीं किया उन्होंने, जो सोल्यूशन चाहिए था वो बनाया, उसके अलावा उस नोजल के थ्रू उन्होंने बना दी। तो हर फील्ड में आपको केक बनाना है, फूड इंडस्ट्री वाले क्या कर रहे हैं, जो डिजाइन की आपको चीज चाहिए वैसा सोल्यूशन बनाया, वो बना के तैयार कर दिया। तो ज्वेलरी वाले हो गया, मतलब क्या क्या गिनों में आपको हर इंडस्ट्री में इतना ज्यादा यूज है 3D प्रिंटिंग का कि अगर आपको एक टेक्नोलॉजी आप ये सीख जाते हैं मैन्युफैक्चरिंग, तो आप खुद बहुत अच्छे एंटरप्रेन्योर भी बन सकते हैं या अच्छी अच्छी कंपनीज को अप्रोच कर सकते हैं। और सबसे अच्छी बात हमारे साथ ये है कि अभी लेटेस्ट इमर्जिंग टेक्नोलॉजी है जो ज्यादा स्टूडेंट्स इस फील्ड में है नहीं, तो जो भी बच्चे इस टेक्नोलॉजी सीखते हैं तो उनको जॉब लगना लगभग पक्का ही है। कल ही हम लोग बात कर रहे थे रौनक चर्चे में, तो वही बता रहा था कि कैसे बच्चों को स्किल्स किया जाए या इस फील्ड में कैसे जॉब अपॉर्चुनिटीज मिलेगी। तो सर इसके बारे में आपको ब्रीफ करेंगे। सो स्टूडेंट्स, मेक द मोस्ट ऑफ अपॉर्चुनिटी। थैंक यू।
Thank you, sir. Now, moving further, I find immense pleasure in introducing our honorable speaker, Mr. Ronak Thimble, who had been serving as an engineer in the field of additive manufacturing for more than 6 years in various companies such as Creative Tools and Components Private Limited, Prognosis Medical System Limited, Versanol Technology Private Limited, and currently he is working as a lead engineer in Wipro 3D.
Wipro 3D was started in 2012, which is a part of Wipro's strategic initiative into the future of manufacturing. Since its inspection, Wipro 3D has quickly grown into a leading provider of metal additive manufacturing solutions and services to the aerospace, space, defense, industrial, and tooling, heavy engineering, healthcare, automotive, and nuclear sectors.
Mr. Ronak Kimball did projects for renowned universities like University of Sheffield from UK and Renshaw Meteorology System Limited from India. He earned a number of certification in courses such as Design for Additive Manufacturing with Metals, treatment of steel, and many more.
His incredible manufacturing tactics helped him to grab an AS's crucial first prize in the cost and manufacturing event held in Italy. His efforts made India to win for the first time in the Formula SAE race.
So, without any further ado, let's welcome Mr. Ron for proceeding over the webinar on metal additive manufacturing processes.
Yeah, good morning to all of you all. Thank you for being here in participating in this session and giving me the opportunity to present. So yeah, today I'll be talking about additive manufacturing and its role in Industry 4.0. I'll just lay down the outline for today's session. First, I will talk about, just give you a basic introduction to additive manufacturing. Focus of this session will be on metal additive manufacturing. Then I'll be covering the design strategies and the design rules that go into designing the components by which they are suitable for additive manufacturing. Then again, a bit about what we do, the kind of setup that we have, a few customer case studies. Again, as Mr. Naman Gandhi pointed out, we do a lot of work for the public sector organizations. So I'll be covering a few exciting case studies. The current research trends, and again, a lot of emphasis was laid on enlightening you on the current job opportunities in this sector. So additive manufacturing, again, as the name suggests, it's a layer by layer addition of material as opposed to traditional manufacturing wherein you remove the material. Those kinds of technologies fall under subtractive manufacturing. And the household term for additive is also 3D printing. So it's very commonly known as 3D printing, and usually the material that we work with is in the powder or filaments. And as you can see on the right hand side, those are the few kinds of parts that we can do use by leveraging this technology. And this McKinsey, which is a global consulting firm in the year of 2013-2014, they announced they had highlighted a couple of technologies which were potentially going to be the disruptive technologies in the next few decades, and 3D printing was identified as one of those 12 technologies. So definitely this technology has a lot of potential, a few pitfalls as well, which we'll be exploring in this session. So this is the process flow of a generic additive manufacturing process. Initially, you have a CAD file, which you generate using any modeling software like SolidWorks or CATIA or NX. Thereafter, this CAD file needs to be exported in a STL format, which is a triangle. I would request all participants to mute all the screens. Yeah, thank you. So thereafter, you export this CAD file in a triangulated STL format. Oftentimes, this triangulation yields some errors. So you do need to prepare the STL file by fixing those errors. And once the file is ready for printing, you slice it. Essentially, slicing is converting the 3D file in 2D slices. So if you have a part which is of about 10 centimeters, you can set the layer thickness and generate the slice geometry for each layer. Once that data is generated, this can be put into the machine, and it can straight away be 3D printed, or the additive manufacturing process takes place. And oftentimes you do need to carry out some post-processing if required. And originally, these three stages, exporting of STL formats, STL preparation, slicing, used to be a different software is to take care of these three functions. But now, a separate file preparation software has been developed to cater to these three steps. So, the process has been reduced to basically just 3 steps. When you have the CAD file, you put it in the file preparation software, and it's ready for 3D printing. And based on my interactions with the industry, I often meet a lot of people, and all of them are extremely opinionated when it comes to additive manufacturing. Certain people believe that additive manufacturing is only suited for prototyping, only for visualizing concept models. And there are the optimistic kind of people who believe that any part should be and can be 3D printed. But the actual real scope of additive manufacturing lies right in between both these thought processes. Additive manufacturing can definitely go, or is definitely suitable for batch or lot production, if not mass production. So we can definitely look beyond prototyping, and because the kind of properties that we get from the parts are just as good as what we get from machining or injection molding. That being said, not every part should be 3D printing, because it does have a few constraints. This is just to give you a brief idea what we are dealing with. So again, mainly it's divided in 2 types of materials, polymers and metals. Of course, there is the ceramic types of material, materials as well. But ceramics mainly work with fused deposition modeling. So the same process can be applied to ceramics, which is why I've not included here. But yeah, when you're working with polymer, work with fused modeling, and the focus of metals is centering. And the focus of this session will be on, so I'll be talking mainly about particle bed fusion, direct energy deposition, and material extrusion. Mentioned, direct energy deposition, you have some form of an existing part or a substrate, and you blow down the powder, and the energy source is incident on this raw material. Again, this raw material can be in the form of wires or powders, and it's usually compatible with hybrid manufacturing. So this comes in handy when we were dealing with oil and gas sectors, wherein the parts are extremely big, and oftentimes they are prone to wear and tear. So many a times certain specific geometries get loose, or the failure occurs very locally. So in order to add material, in order to replace this part completely, what people now or industry nowadays is doing is essentially adding the material in that section itself, and carrying out any machining processes after the additive manufacturing. So it comes in it's really compatible with hybrid manufacturing. Material extrusion, again, it's similar to FDM or fused deposition modeling, wherein the material is extruded through a nozzle, and thereafter this material is in the form of a binder and the metal. So pure metal cannot be extruded very easily, so because you require very high temperatures. So binder and metal, again, the melting point comes down, so extrusion becomes easier. Once you extrude the part, you carry out the debinding and the sintering to end up with the pure metallic part. And powder bed fusion technologies, again, wherein the energy is incident on the powder bed. So you have a sort of a, so yeah, you have a powder bed, and the energy is incident on the powder bed. And the process, again, the part is getting built layer by layer, and this energy can be in the form of a laser, electron beam, or the sintering cycle. So I'll be talking mainly about powder bed fusion technologies, and the reason for this is that 70% of the metal additive manufacturing market is being occupied by powder bed fusion technologies. And the reason for this is this came early into the market, which is why they are established processes and continually in the state of continuous improvement. Because they came early into the market, machine costs are decreasing over the years. These machines operate with open parameters, so we have the flexibility to set our own parameters when you're processing the material. And because of this flexibility, we have the ability to attain custom part properties, which again, we do not have the liberty to do that when we work with material extrusion or when we work with direct energy deposition. We are restricted with a lot of these things, and which is why powder bed fusion technologies are usually preferred. And they can be sector agnostic, part agnostic applications can be carried out using this technology. And three machine sets can be identified under powder bed fusion technologies, namely direct metal laser sintering, electron beam melting, and binder jetting. So just to give you a brief overview, I'll be covering the principles of each of these in the next few slides. But in direct metal laser sintering, you have a terbium laser, which is incident and which consolidates the powder material. And again, the material is getting added layer by layer. The powder bed, the build bed, essentially gets lowered layer by layer. And we are working with inert gases when you are working with direct metal laser sintering, which is also known as laser powder bed fusion. And a few of the machine manufacturers are EOS and Renishaw. We ourselves use EOS machines, who are the pioneers in this technology. Electron beam melting, again, is very much similar to direct metal laser sintering, but instead of a laser, you're using an electron beam to serve the same function. As opposed to inert gas, you're working with a vacuum chamber and electron beam melting. And binder jetting, again, is completely different from these two, wherein you are depositing the binder on a powder bed, and then you carry out the sintering to come up with the part consolidation. So in a way, it's similar to material extrusion because you are carrying out the sintering cycle. But again, it's not at all similar to what happens in direct metal laser sintering or electron beam melting. And there is the ability to incorporate this technology on a desktop grade machines as well, which is very office friendly. So this technology is up and coming. Firstly, I'll be talking about electron beam melting, wherein you have a tungsten element and the electrons are emitted from this tungsten element. Nowadays, they often use single quartz crystal, and these electrons, they get accelerated to an anode, and then they're incident on the powder bed, and the energy that these electrons carry is in the form of kinetic energy, which it's converted into heat energy when they collide with the powder particles. And this process can be characterized by 3 stages of melting. So firstly, you have the entire bed getting heated, which is known as the preheating theme. Then you have the contour melting, which is known as, which is mainly the part boundary getting melted. And then you have the hatching, wherein the part geometry gets melted. And after each melting cycle, the powder bed gets lowered by a layer thickness, which is a parameter that we can set. And it's interesting to note that all of these melting actions are taken care of by an electron beam. Again, so now I'll just show you a brief video about what I was talking about, the process.
Additive manufacturing offers greater freedom in design and allows for the creation of optimized parts that are not constrained by the limits of traditional manufacturing. RCAM EPM has the unique ability that tightly stack parts within the build in order to increase productivity. An optimized build file is sliced, then loaded into the RCAM EPM system. Following this, metal powder is loaded into the machine. The build chamber is then closed, and a vacuum is created to ensure a clean, controlled environment that allows for the processing of reactive material. Next, RCAM EPM's powder layering system evenly distributes a thin layer of powder on the build area. A powerful 6 kilowatt electron beam heats the powder bed to the optimal ambient temperature and then proceeds to melt the powder. First, contour melting and then edge melting. The electron beam unit generating the beam contains no moving parts, allowing for extremely fast and accurate beam control. The build environment is kept hot, reaching temperatures exceeding 1000 degrees Celsius, resulting in no residual stresses and allowing for the processing of crack-prone materials. As each layer is completed, the build is lowered and a fresh layer of build powder is raked over it. This process repeats, pouring the build one layer at a time. When the build is complete, the tank is extracted and the RCAM EPM machine is prepared for the next build.
So now we're talking about metal binder jetting, wherein we are working with extremely fine powders for the raw material. And as I mentioned in the earlier slide, you have the binder, which is deposited as per the slice geometry. And once the deposition is taken care of, this bed again gets lowered by a layer thickness, very much similar to electron beam melting. So we can say that again, 3 stages of processing. Firstly, you apply the binder, and once this binder, because it's in liquid form, you need to dry the binder so that the next layer can be applied with more stability. So this drying process takes place just immediately after the binder is applied. Once the part is printed, you cure the part or debind the part, or debinding process takes place. And once the curing process is over, you sinter the part, or oftentimes optional treatment is carried out in the form of infiltration. So again, just to show you a brief idea about the process, very much similar to what we do with electron beam melting in terms of how the powder bed gets lowered layer by layer, but definitely different in the working principle. Now, again, I'll just show you a quick video about laser powder bed fusion, which again, I'll just try to explain it as the process is going. So this is the melting stage, wherein the laser is incident on the powder bed, melting the powder particles as per the slice geometry. So the movement of the laser is taken care of by the optics, which are set up in the machine. And interestingly, SLM works with heaters which are fitted on the bed on the base plate, which is unlike electron beam melting, wherein electron beam melting itself takes care of the preheating, which is on the bed. So now the recoater goes back, it deposits a new fresh layer of powder, and during this process, the bed gets lowered by a layer. So this layer thickness is common in all of these powder bed fusion technologies, which again is a material dependent value. It needs to be set as per whatever kind of material and kind of particle size distribution we are working with. And essentially the part gets built like this, layer by layer, and once it's over, you allow it to cool down because you're working with such high temperatures. You do not want to bring in any residual stresses or warpage. So yeah, similarly, it's not noticeable, but it's gone down by a few microns of layer thicknesses. And once the part is finished, you remove the part, allow it for some time to cool down, and you have a part which is fixed on the bed plate. So of all the three technologies that we saw, laser powder bed fusion has its benefits. Firstly, it has the widest material capability. So when you want to work with exotic materials like gold or even materials like bronze, copper, laser powder bed fusion gives us the most consistent results. So that is what I mean by repeatability. Oftentimes, these machines can be erratic in terms of what we want as an end result in terms of the mechanical properties. Since we are working with powder-like material, it's very difficult to predict how the powder is going to integrate itself in building of the part. So, but that being said, laser powder bed fusion gives us the most repeatability, better accuracy and feedstock reusability in terms of EBM, because as we saw in EBM, the entire build plate gets heated to 1000 degree Celsius temperature, as opposed to the infrared heaters that we have in laser powder bed fusion machines, which operate somewhere around 200 degrees Celsius. So definitely a better accuracy, and we are able to use more of the powder, which is the remaining powder, apart from what is getting melted. And the laser diameter is definitely smaller than the electron beam, so we can process lattice geometries or honeycomb geometries that we see in the parts oftentimes when we are working with additive manufacturing. So when we compare it with electron beam melting, yes, it's definitely less aggressive, and we have a better throughput when we are working with materials like titanium or stainless steel and aluminum. Aluminum definitely cannot be processed using electron beam technologies because we are working with temperatures exceeding 1000 degrees, and the melting point of aluminum is somewhere around 600, 650 degrees Celsius. And when we compare it with binder jetting, oftentimes when we put it in the sintering, the binder is removed completely and the oftentimes we meted into the part. Sometimes we because this binder has volume. Again, when you are building the parts using binder jetting technology, you need to apply these shrinkage allowances to accommodate for what we want in a final part. It's not an empirical relation with the amount of binder that we are using, but it just comes with trial and error what we want in the final part. So all these estimations of shrinkage or allowances are not required when we work in laser powder bed fusion. And yeah, just again, a comparative analysis between all these three technologies. So as I mentioned, the energy source for DMLS is laser. For electron beam melting, it's the electron beam, and in case of binder jetting, it's the sintering. Material capability, again, it's the widest when it comes to direct metal is sintering. As I mentioned, electron beam melting, we cannot process aluminum alloys or zinc magnesium alloys. And binder jetting, again, we cannot use it for titanium and exotic materials. Minimum feature size, again, DMLS comes out in favorably. Mechanical properties in DMLS are good. Electron beam melting, again, good. Binder jetting properties, again, they're not ideal because the sintering cycle does not guarantee complete densification of the part. That being said, binder jetting operates at a much higher speed if you compare it with DMLS or EBM, and the machine hour rate from usability point of view. So the kind of machine hour rates that we work with DMLS again are on the lower side, and we can try, since all these machines work with open parameters, we have the flexibility in choosing whatever raw material that we want of whatever size, depending if we have the right kind of parameters for them. And accuracy that we get with DMLS again comes out in a better way, and the amount of supports that we require. That being said, the amount of supports that we require for DMLS can be on the higher side because we are not working with high temperatures as what happens in electron beam melting. So there is a possibility of a thermal gradient being set up because we are rapidly heating the powder to melt it and rapidly solidifying it. And once we have this thermal gradient, this can lead to possibility of buildup of residual stresses, which if not catered to can lead to significant warpage or delamination in your part. So you do need to add the supports. I'll be talking about this section in the next few slides. So we can work with three strategies when it comes to implementing additive manufacturing, namely replicate for additive manufacturing, secondly adapt for additive manufacturing, and thirdly design for additive manufacturing, or DFAM, which again is being talked about in the industry. So when it comes to replicate for additive manufacturing, you are merely printing the same part which was designed for conventional manufacturing or traditional manufacturing. You're simply 3D printing it, and you're able to. It's useful in comparing the results what we get from 3D printing and setting up benchmarks. Comparative study between the two manufacturing techniques. And it can be an extremely value-added tool in new product development activities. So oftentimes we have a design concept, we have a design, but before rolling it out for mass manufacturing, we want to test it out, a simple prototype. So this is where the prototyping front of additive manufacturing or 3D printing comes to the forefront. And its ability in just quick part manufacturing, and in case of immediate requirements of the part. So when you're working with oil and gas sectors, or other critical the medical sectors, wherein parts are usually required in cases of emergencies in a couple of days or a couple of weeks, 3D printing has the ability, or this strategy, replicate for additive manufacturing strategy, has the ability to give the end use part right away. So this is where this strategy comes in handy for these kinds of applications. Secondly, yeah, we have adapt for aim or adapt for additive manufacturing, wherein we have the flexibility in altering the geometry and the material. That being said, we cannot change the mating interfaces and the functional features. So in case whenever we have a conventional assembly or conventional part which is designed for conventional manufacturing, it will be serving a specific purpose. So all of the dimensions which are incorporating to serving this purpose cannot be altered in this strategy. We can only work around the design space surrounding these features. And again, the strategy is handy when we want to reduce the amount of post-processing. Since we are working around the area around the functional area, we have the ability to bring down build time, overall cost of the part, and with these themes, we can get an enhanced performance. And for incorporating this strategy, you do not require any specific generative design tools. It's simply about applying a few design guidelines, which I'll be talking about in the next few slides. And this is where additive manufacturing technology completely thrives, because it's a part which is completely suited for additive manufacturing. You remove, you are not restricted by any form, fit, function restrictions. You start afresh and coming up with the design for the part and to serve the function. And this is where the technology completely thrives. And oftentimes you do require advanced softwares, generative design or computational design softwares to come up with such intricate designs. And you need to identify the constraints and the boundary loading conditions in, again, setting up of such a design, which comes up organically once we put in our constraints or our boundary conditions in the software. So it can be seen that it forms a pyramid of a sort, with replicate for additive manufacturing being at the bottom of the pyramid, which offers production benefits in terms of lower tooling costs, shorter process times, shorter lead times. If you go up higher in the pyramid, we can try to consolidate the parts together which can result in bringing down the weight, faster product launch, more reliability, better performance. But when we apply the DFAM strategy, that is where we get the maximum benefits on the financial and the production on all fronts, essentially. In because by incorporating the strategy and coming up with a component, we are ensuring that this product or this part or this assembly cannot be manufactured by any other technology apart from additive. Now I'll just go over a few elementary design rules that we work with. So as I mentioned, supports are often required, and occasionally overhang sections which are more than 0.5 or 0.7 mm, they require supports. And the purpose of the supports is to anchor the part of the substrate, and they also act as heat sinks because we are working with such high temperatures. I mentioned in the earlier slide that the thermal gradient gets set up, and these supports act as heat sinks in transfer of the heat away from the part, and trying to manage the thermal aspects of this process. And understandably, supports add extra cost to the build, and they must be removed once the print is complete, because they might hinder to the part functionality. And often these supports are removed using some post-processing technologies, whether that's polishing, whether that's manually, whether that's machining. So this slide is again, I've introduced this to drive home the point that additive manufacturing cannot be the answer to everything. There may be some parts wherein we do not want to incorporate, we only want to incorporate the replicate for additive manufacturing strategy, which may have a lot of support structures in whatever way we are orientating it. So definitely due consideration must be given in understanding what part should be 3D printed. So it's not like all parts should be 3D printed. Oftentimes we cannot, some parts may not be suitable for 3D printing. So these are a few design changes that we can try to incorporate when you're working with additive manufacturing. Oftentimes you have these overhangs, and the section that on the left you can see that's requiring supports. But if we simply add a chamfer which has an angle exceeding 45-50 degrees, that section becomes support free. So this is something that we can incorporate in our design in non-functional dimensions, an element of adapt for additive manufacturing strategy. And occasionally, if we cannot do that, on the right you can see we can orient the part in such a way that the supports are minimized. So in case of the T, which is kept in that in a horizontal manner, you have the supports which are protruding on the left and the right of the T. But if you just simply anchor it to, if you place it in an angle, the support requirements reduces. So all of these are aspects of additive engineering which are taken care of in the file preparation software, what I was talking about in the process flow. So these are the different kinds of supports that we can put in. We can put in the block supports, supports with perforations, and occasionally we can even work with tree supports. Again, this depend on material to material. Since aluminium is a relatively lightweight material, and we have incorporated tree supports in those kinds of parts, when the weight of that section is lower. So that's where we can try to bring in tree supports, which are definitely more effective in support removal and driving down the process cost. But oftentimes we cannot bring in tree supports when you're working with extremely long supports and materials which are more dense, like steels. So that's when we cannot use these kinds of tree supports. Then we have to go with block supports, which need to be removed once the print is over. So yeah, holes again, drilled holes or holes cannot be 3D printed if they exceed a size of 10 millimeters. If it's anything below 10 millimeters, we can print it, but again, that sinking effect can be observed in such holes. So what we can try to introduce are ellipse geometries or teardrop or these diamond shaped geometries, which are self-supporting cross sections, and these sections can be machined later on. So in case we want to avoid the sinking effect at the top, as you can see in the image there, we would require to add supports, which again would need to be removed later on. But instead of that, we can try to work with this ellipse or teardrop or diamond shaped geometries to have no supports at all. And as I mentioned in the earlier slide, no supports would mean lower cost and a faster processing time for the part. Occasionally, we can print hollow sections, hollow cubes, which are of a specific thickness. And since due to the nature of the process, it's only going to selectively melt the powder as per the geometry. So it's not going to melt the powder which is inside this hollow geometry. And which is why these escape holes are required in the geometry, because if we do not put these in, the powder will get trapped inside these hollow sections. So it's important to add such holes when you're working with uh, hollow geometries, which again do not hinder with the functionality, and the minimum diameter that is required is somewhere in the range of 1.5 to 2 mm. And the minimum features that we can print, or the minimum wall thicknesses that we can work with, is 0.3 mm. So oftentimes when we're working with bulky parts, which are designed for casting or other conventional manufacturing techniques, uh, you know, we are limited with the minimum wall thicknesses. Like for example, uh, in the best of casting processes, the wall thicknesses can be as low as 5 to 6 mm, and that's just from a processing limitation. But in terms of 3D printing, we can take down the wall thickness by as low as 0.3 mm. Again, very much similar to what we see in the industry, is that we should always try to add fillets and chamfers wherever possible, because as you can see on the left hand side, sudden changes in the geometry can bring in residual stresses, which again are deleterious from the part functionality and processing capability. And even if we are adding fillets, they should be limited to, especially downward fillets, they should be limited to less than 2 mm, because if they exceed this value, we would require to add support. So again, we would require to add supports. So there should be a balance in setting up of these fillets and chamfers. And again, chamfers are a unique capability of 3D printing, because we are working with extremely fine lasers and extremely fine powder, and oftentimes incorporate these in our designs and drive down the wall thicknesses. So in case we have a bulky part of 5-6 mm thickness, we can make the wall thicknesses 0.3, 0.5 mm and introduce these lattice structures inside the geometry, which should drive down the weight and increase the stiffness of the part, which can be useful in the aerospace or sectors which require the parts to bring down the weight from a functionality point of view. Now I'll just go over the kind of setup that we have and a few of our projects that we have undertaken. So we offer end-to-end support to our customers. First, we start with the consulting, which often includes identifying the components which are ideal for 3D printing, setting up of the strategy, prototyping and manufacturing services as per the customer requirements, R&D solutions, and even setting up of captive aim centers, which I'll be talking about. We carried out such an exercise for SAC, which is under ISRO. So our journey in additive started somewhere around 2012, 2013, wherein we set up capacity, and slowly and surely we tried to incorporate each functionality. So we brought in our design for AM capability in terms of experienced engineers. Then we set up a post-processing capability, which is often required because, as I mentioned, you do require to remove the supports or machine the parts. And once all of this was set up, we went into R&D, testing of the material and the testing of the parts, and also design services. So as sir mentioned, critical sectors like aerospace and healthcare are definitely looking out for introducing additive manufacturing in some way and form. So they are the main drivers for this technology. But that being said, again, automotive and oil and gas, we have been able to work with major OEMs, and even industrial and tooling applications have been identified for 3D printing, which we have been able to tap into. So yeah, just a brief overview about the kind of capability and setup that we have here. Approximately 12,000 square feet, and 3 machines we have, one of which is the M400, which is a build volume of 400 by 400 by 400, and we are planning to set up a DED and a binder jetting machine sometime in the near future. And the post-processing setup, again, a complete detailed setup, right from furnace to wire cutting, surface grinding, machining, wherever required. And for our testing of the powders and the parts, we have the particle size analyzer, microscopy, ONH analyzer, which is essential because when you're working with materials like titanium and aluminum, which have a very strong affinity for oxygen, it's important that these oxygen values are kept to a minimum during processing, because if they get introduced in the part, they can form oxides and compounds which will lead to premature failure of the part. Just to images of our setup. So yeah, these are a few of our customers, which mainly cover a lot of public sector units. We worked with GE on many wings of GE, a few automotive companies as well, a few exciting startups like Skyroot Aerospace and Moog Aircraft, Ather as well, which is one of the electric two-wheeler companies. So this is one of the case studies wherein we helped SAC in setting up of a captive center, wherein we consulted with them. We identified which machines they need to buy, what kind of powders they need to procure, training of their scientists. We even stationed one of our application engineers in their offices, and he worked with their scientists in developing of this part that we see here, the northwest feed cluster. So on the left hand side, you can see the part which was welded together. It was coming together in 12 parts, this assembly, which was welded together, which was reduced to a single component by the design that you see on the right hand side. And as you can imagine, RF devices or radio frequency devices, they often are prone to attenuation loss when we bring in an assembly of components which are coming together by welding technologies. But a single component is very, very effective in its performance. So this is where our technology and our experience really helped SAC in coming up with this component. And this exercise took a period of about 1.5 to 2 years in coming up with this component and training all of their engineers and scientists team in carrying out a continued production of this component whenever they require it. And yeah, it's we're proud to say that it's India's first metal AM functional component, which is currently in orbit. I believe somewhere around 2018 they had carried out the testing, and all the 4 feed horns were successfully cleared for uh, the orbit testing. So again, this was a component for another public sector organization, which was an altimeter assembly of 4 parts, and we redesigned it in such a way that would be suitable for additive manufacturing by bringing down the weight, and again bringing with wall thicknesses as low as 1.2 mm, which would be very difficult by machining or by casting. So definitely we are able to add tremendous value to our customers by leveraging this technology, and by simple few design alterations we're able to enhance the performance of the components which would have been realized via conventional manufacturing. So this is a very interesting application in the tooling sector. So currently, conformal cooling is a very popular concept when you are working with injection molding cores and mold inserts, wherein the cooling channel is as per the geometry of the part that is 3D that is going to be produced. So it's not that the part is getting 3D printed, but it's the tooling that is required to bring out the part is getting 3D printed. And when you're dealing with those kinds of curved geometries or those curved pathways, you simply cannot machine them or conventionally manufacture them. So this is the unique capability of 3D printing, wherein the tooling industry are trying to bring in for parts which are extremely of low wall thicknesses and which are prone to warpage delamination during injection molding cycles. So definitely this is a very unique application for 3D metal 3D printing. And again, DMLS comes out in favor because of the fact that relatively the surface finish is on the higher side, and mechanical properties, the kind of hardness that we want is somewhere in the range of 60-62 HRC when we are working with maraging steel. So it requires to be heat treated, but again DMLS comes out in favor when we are working with these kinds of parts. And interestingly, we can try to incorporate this with with machining. So sections which do not require those complex designs, they can be conventionally manufactured, fixed on the base plate, and only the section which is having those complex cooling channels or those curved cooling channels, they can be 3D printed. Now you may ask that, well, direct energy deposition is compatible with hybrid manufacturing, but you should know that direct energy deposition machines are suited for big parts. So parts which are in the range of exceeding 600 mm by 600 mm by 600 mm. So they will not be entirely suitable for parts which are used in these cores and inserts. Now again, as sir had mentioned, I'd like to talk about the kind of job opportunities that are available. Firstly, again, top of a list is the design engineering, which is appealing to all mechanical engineers. What we saw in a few of the design rule slides that I put in, that is the design for aim methodology, or applying those rules in realization of the part. Again, it should be as per the customer requirements and the inputs that you get. And once this part has been realized, you need to carry out a simulation in the operating environment. So even though you have the part, it's not as simple as putting the CAD geometry and ending up with the as required geometry. You need to simulate this design for checking of the delamination and warpage, because as I mentioned, if you are working with selective laser melting or direct metal laser sintering, we are working with a lot of residual stresses, and this thermal management can become difficult. So before putting it in the machine, we would want to simulate the part build in the operating environment based on whatever parameters that we have set for the operation of the build. Thereafter, you have the application engineering, wherein the file preparation for the respective part. So in what way we want to orient it, in what way you would want to support it, I mean add the supports, and the respective machining allowances wherever machining is required for the part. And again, the build simulation and validation for the set of process parameters. Manufacturing engineering, again, planning and scheduling. So these machines are operating, they do not require an operator as such, but when you're working with consecutive builds, you do need to plan your activities in such a way that your builds do not accommodate a lead time, and you need to identify what build should go on first, and a sequential flow as to which builds should be catered for. And once the part is fitted in the machine, you do need to think about the loading of the part, the loading of the powder conveying and sieving after the build is over, filter system. Because these machines work with filters, you do need to think about after how many number of builds you would want to replace this filter. The recoater, which is depositing the powder, the recoater setting also should be ideal, because if it's not depositing proper layer of powder, you will end up with porosities in your parts oftentimes. And the kind of build platform that you'll be selecting, depending on the part geometry, if it's a heavy part, you will want to go with bigger or build platform of a higher thickness. And again, workflow execution as per requirement. So after 3D printing it, what is it that is going to happen? So you may carry out stress relieving, you may carry out, once you do the stress relieving, you may want to put it in iridium to remove it from the build plate. After that, if you want to carry out polishing or any surface treatment techniques or machining, so all of that execution comes under manufacturing engineering, and it's important to do it as per the requirements. This is where our knowledge of conventional manufacturing comes in handy. So it's not that 3D printing is going to completely replace the way we do things, but it's going to work with traditional manufacturing in serving our end goal. Materials engineering is very exciting, which may not be a major element of mechanical engineering, but is very much required. A few of our mechanical engineers are working in this domain in our company, because say we have process parameters for a set of process parameters for aluminum, but we want to carry out process optimization in such a way that the amount of time it requires for printing is brought down by 20-30%. So we do need to change our parameters in such a way that these goals can be met, and the validation of these process parameters is taken care of by our materials department. So if we modify the parameters in a certain way, we would want to see what is it that we are ending up with before printing the final part. So we have a few metallurgists who look after that. Material development, again, the team looks into that as well in case of new materials to be developed. So currently we are limited with the kinds of materials that we can process for additive manufacturing, and we do need to introduce more and more materials which are available in the market for conventional manufacturing. And they are also in what is going to be the post. Often there are processes like heat treatment or hot isostatic pressing, or cold isostatic pressing, wherein we want to alter the microstructure, whatever we get from 3D printing alone itself, to meet the end user requirements, because it's very difficult to get the required, oftentimes it's in critical applications it's difficult to get the required properties using only 3D printing. So they can step in and suggest what kind of heat treatment cycles you would want to set for the respective part. And lastly, quality engineering again. Powder feedstock, very important to check whether this powder, whatever it's being used, is it ideal for 3D printing, whether it's conforming to the particle size distribution, which is mentioned by the manufacturer, whether it has those limited amounts of oxygen, nitrogen, and hydrogen, whatever we carry out in the ONH analyzer. Before printing the final part, we can carry out certain destructive and non-destructive testing methods on test coupons as per ASTM standards to ensure that the parameters are extremely fine-tuned. And again, all of this process flow should be as per the ISO A standards, so that no lack of communication is there in terms of what is being undertaken at this stage. The team should be in complete understanding. And once the part is printed, we would want to carry out the dimensional inspection, whether it's within those tolerances that the customer is requiring. So this can be done using the CMM setup or the scanning setup. So again, to drive home the point that 3D printing alone will not be able to take care of all of these things. It's going to be in accordance with what is available in the conventional and traditional manufacturing. So yeah, the current research trends, we are developing a machine itself in collaboration with IISc Bangalore. It's an electron beam melting machine. We have identified a requirement for this with our customers from aerospace who want to work with refractory materials like tungsten or niobium, and we are trying to the available commercial systems are working with 6 kilowatt electron beams, whereas we are targeting 10 kilowatt electron beams for the processing of the material. And hopefully we should be launching this machine sometime later this year. And as I mentioned, the specific interest in the industry right now is to try to process refractory elements like tungsten, tantalum, and niobium. Tungsten especially has a very high hardness and has been identified as ideal candidate for nuclear fission reactor components because of its very high melting point. Niobium again has the lowest density and has been thought of been put into particle accelerators which utilize superconducting radio frequency resonant cavity devices, which ensure a very high quality factors and storing the energy at very low rates, very low loss rates. And tantalum is a biocompatible material. Even though it is slightly more dense than titanium, it can be utilized for less elastic kinds of medical devices, and its luminescence in X-ray. So it's X-ray imaging is very easy when we are working in tantalum materials. I've experienced this firsthand, wherein we were manufacturing implants using titanium, but the doctors were fixing these implants using tantalum pins, and the fitment, to ensure that this fitment was done in a proper way, tantalum was used in those pins, so that the fitment would be checked by estimating as to how these pins are fit or how these pins are positioned after the surgery. And also high entropy alloys, again, these are a novel class of metallic alloys which are constituted of 4 to 5 equimolar elements with no principal element as such. And with the solute strengthening effect, that's the source of its strength, which again has been identified and suitable for additive manufacturing because of the high cooling rates that we work with. It's not suitable for traditional manufacturing or powder metallurgy techniques, but instead for additive manufacturing. So yeah, in summary, main 3 points I would want to highlight is additive manufacturing will not be replacing traditional in any way. It will work in unison. Design for additive manufacturing is the single most important tool in unleashing the true potential for additive. And selective laser melting is possibly the most versatile of all metal EM technologies, which is what makes us sector agnostic and application agnostic, because we have the capability to process a wider range, a wider array of materials using this technology. So yeah, that concludes my session for today, and thank you all for being here, and definitely I would be open to answering any questions from the audience or from the faculty members.
Thank you, sir. We are grateful for the time and efforts you took to share your thoughts and experiences. Now, if anyone having any doubts can drop messages in the chat box or unmute yourself and can read out verbally.
Sir, there is a very buzzword in market like manufacturing is going to digitalize. So how you say?
Sir, could you repeat your question? आपका आवाज थोड़ा ब्रेक हो गया.
Yeah, actually एक word काफी ज्यादा बज में है market में. It is like the manufacturing is going to digitalize. So what is digital manufacturing?
Digital manufacturing, oftentimes we have the part, but we do not have the CAD drawing. So nowadays, in many situations, we are using scanning technologies to come up with the 3D CAD design. Once we have the 3D CAD design, as we saw, it's ready for 3D printing. And once it's 3D printed, then we can remove it and put it ahead for end use or post processing requirement. But up until this 3D printing, it's not least amount of human intervention is required in coming up with the design of the part. So this is what is can be summarized as digital manufacturing, wherein we are leveraging these advanced technologies and realization of the part.
Students, कोई भी अगर आपकी क्वेरी हो तो आप उसको चैट बॉक्स में लिख सकते हैं या डायरेक्टली अपने आप को अनम्यूट करके पूछ सकते हैं. We'll wait for 30 seconds more. अगर किसी को भी कोई क्वेरी हो तो आप लोग टाइप कर सकते हैं या पूछ सकते हैं. This is a golden opportunity for you all.
Sir, you can even share my email ID with your students. They can reach out to me anytime they want, and it's not like it's required now itself. Not a problem. I understand a lot of data was being shared, so it can take some time to assimilate, sir. And in chat box, or you can even reach me my mail. I forgot to attach it. I hope Mr. Gandhi has my mail ID, so he can definitely share it with all of his students.
Sure, sir. Sure.
Hello. Hello.
Yeah, KK Sahu, sir.
Hello. I have a question, sir. Can I ask you some question, please?
Yeah, sure. Go on.
Hello, sir. I'm Professor KK Sahu, and presently I am working in additive manufacturing, basically in the medical field. So presently I am working in the bone scaffolds, and as far as concerned material concerned, I am using the ceramic materials. Can you suggest me that for short-term implantations, which material, metallic materials are suitable for the scaffolds? Because in the literature review, I have just changed the titanium, palladium are mostly used in the scaffolds, but they are in the long-term basis. So which type of materials are basically presently now available for the short-term reasons in particular in the bone scaffold?
A material by the name of PEEK, which is an abbreviation of polyether ether ketone, is often used in bone scaffolds because of its similarity with the bones, the structure. So it's a
But
polymer.
PEEK is
It's
considered as a yes, it's a polymer. I am talking about the metallic materials. Basically,
metallic.
the stainless steels. Yes.
Stainless steel again is
Stainless steel,
was
titanium,
used to,
alloys are
right,
generally mostly used, but they are not degradable.
right.
So
Okay,
can we
I
move?
understand. So, in such applications, I would have to get back to you on that front because I do not have that information firsthand. But yeah, I'll definitely look
Okay.
into that matter and get back to you.
Yeah. I will
Thank you,
share
sir.
the email ID in the group, so you can ask sir questions by mail also. We have a short of time. So,
Sir, I have one question related to material. If you permit me to ask.
Sure, go on.
Sir, I just want to know the means if we are using a metallic 3D printed component and there is a conventional material. So what is the difference? Means how we are going to compare the strength of these two materials? Means uh, whether these 3D printed parts are having sufficient strength compared to the conventional material which we are using?
Yeah, it's a very good question, which I forgot to mention in the seminar. So if you compare properties like tensile strength, yield strength of equivalent materials, what you get from 3D printing, metal 3D printing is slightly better than what you get from castings or forging. But if you are looking at elongation or ductility properties, it might be poorer in terms of 3D printing. So it depends on what your end use requirement is. You can always carry out some heat treatments to bring out the required properties. But just to give you an idea, an as 3D printed component, if you compare it with casting component, in terms of certain mechanical properties, it will be better. Again, if you compare 3D printed part with forging, it will definitely be on the lower side in all parameters, because forged components are considered of a very high hardness and very high strength. But again, it lies somewhere between casting and forging in certain mechanical properties.
Okay, thank you, sir.
any more question? Okay, Shivangi, you can proceed. No.
Thank you, sir. Now I would like to call our Honorable Principal, sir, with his encouraging words.
Good morning, everyone, and good morning, speakers. In today's expert speaker, I want to thank our expert speaker for giving lecture on such a important topic to our students. And also, I want to thank our organizing team for conducting this session. Though I'm not from this field, but I know additive manufacturing is the future of manufacturing, and it is nowadays most popular manufacturing technique. And so I want to congratulate our students also for participating in this event. And I want to tell that some of your seniors have made one 3D printer model, and it is available in robotics lab. So you can try some models by using that 3D printer. Okay, so thank you once again to all of you, and thank you, speakers.
Thank you, sir. Now, I would like to call our head of department to give a vote of thanks.
Thank you, Shivangi. And first of all, I want to just thank a great thank to the speaker, sir, Mr. Ronak. And he has just gives their precious time for motivating, and just they have given very good knowledge to our students. And especially thank to our DG sir, they have motivated to us for conducting such kind of the seminar. And our principal sir, every time they are guide us for conducting this type of the activity. And we will take the help in future also with the Ronak sir. And I also just appreciate the patience of our student. Thank you, Ronak sir, and thanks the last Mr. Naman and his team. Thank you, sir.
Thank you very much, sir. Now, with this, I would like to conclude this session.
Yeah, thank you all for being here. And you can reach out to me anytime. And we are looking forward to establishing a long-term relationship with your college. So yeah, thanks for giving us the opportunity to present here. And yeah, we'll
Thank you.
keep in
Thank you
touch.
so much.
Thank you, sir. Thank you. Okay.